The next idea we are going to discuss is work done by the force of gravitation between two objects. Okay, we'll start with point masses. Consider a system like this. Let's say there are 2 point masses, m1 and m2. Let's assume one of them is fixed. Okay. These two particles or point masses, assume they are initially at a separation x1. Okay. M2, let's say, is taken from this position A to some other position B. For now, we will assume it moves on the straight line connecting these two particles. Later, we'll generalize the result. So let's say M2 is taken from A to B. Okay. Now it's undergoing some displacement. And as M2 is taken from A to B, now who is taking it? Some external agent. Okay. By some means, it is being moved from A to B. But as M2 moves from A to B, M1's gravitational force would be acting on it. It will always be acting. We will derive an expression for the work done by that gravitational force. Okay. Initial separation between them, let it be x1. Final separation between m1 and m2, okay, when the displacement is complete, let's say the final separation is x2. So during this journey, what is the work done by gravitational force between them is what we need to derive. Fine. One of you quickly tell me, what is the basic formula for work done by a force? Okay. General formula for work done by any force is integral F dot ds. Correct. If the force is constant or uniform over the entire displacement, then you can use F dot S. But it is variable, you will use integral F dot ds. Now, one of you tell me, as the particle B, okay, as the particle M2 is taken from A to B, okay, as it is moved from A to B, do you think the force between these two masses will be uniform or it will change from place to place? Vanilla, don't answer. Anyone else tell me. During this displacement, will the gravitational force be constant or variable?
Sir, constant.
Rishi, what are the factors on which gravitational force depends between 2 point masses?
Between 2 point, yeah, it'll be different, sir. The more the distance, the lesser it will be.
Correct. So, see, general question. General way of answering. You were asked whether the gravitational force will be constant or it varies. Then naturally you have to think of the factors on which that quantity depends. And you know gravitational force between 2 point masses depends on the distance between them. So the force is a variable force. Okay. So the formula you have to use to calculate work done is integral F dot ds. And integral F dot ds can be written like this. Magnitude of force, magnitude of displacement, cos of the angle between them. Okay. This is what we need to integrate. Okay. Since the force is variable, what we will do is we will consider a random instant during the displacement. Okay. At a random instant, let's say the separation between the particles is x. At that instant, we will write the expression for force. Okay, you all have to do this. First, write the expression for force. Next, assume some displacement ds. Now it is being taken from A to B, so you know how it is being moved. So visualize displacement and try to express it. Means try to express ds in terms of dx. Why do you need to do that? Because force is going to be in terms of x. So in order to integrate properly, you need ds in terms of dx. Okay, try to do that. They may be equal, they may not be equal. You have to think about it. And then visualize the angle between force and displacement also. How much will it be? Substitute all of them in the integral and integrate with limits from x1 to x2. Try to do this, all of you. I'll give you 3 minutes. After that, we'll discuss. So write the formula for magnitude of force at that random instant. Try to express displacement in terms of dx, and then substitute everything in that integral formula and integrate. Okay, listen, all of you. As M2 is taken from A to B, okay, you know how it is moving, that's fine. Can one of you tell me the direction of gravitational force acting on M2? Just the direction of the force.
Towards M1.
Towards M1, good. So at any instant, the force acting on it will be this way. Okay. And it is moving to the right. So at any instant, the small displacement it undergoes will be this way. ds. Now, as it is taken from A to B, the force is inwards. Inwards means, what can I say? It's an attractive force. No, it is towards M1. But the displacement is outwards. The distance between them is being increased. Therefore, the work done has to come out negative. So whatever answer you get, once you substitute x1, x2, x2 being greater than x1, it should become negative. We'll see. Now, at a random instant, when the distance between them is x, the force acting between them, magnitude will be g m1 m2 by x square. That's the force. Next, if you visualize the displacement, since we have considered a case where the particle is moving on the straight line connecting the two particles, the ds, displacement ds, or the magnitude of the displacement ds, will be the change in the value of x. Whatever displacement it undergoes, by the same amount x will increase. So you can write magnitude of ds as dx. Okay, hope you all understood this point. If there's any doubt, you can ask. So force is g m1 m2 by x square. Magnitude of displacement is the change in x itself. Okay, and see, m2 is going away from m1. As m2 goes away from m1, x increases. If x increases, dx will be positive. Generally, any quantity which is increasing, d of that quantity will be positive. And we are writing magnitude of displacement as dx. Magnitude of a vector should never be negative. Okay. And here we have ensured that dx is a positive term. So in place of modulus of ds, magnitude of ds, you can write dx. Next, angle between the force and displacement. At any moment, the angle between the force and displacement will be 180 degrees. Cos 180 is -1. Okay. Now we'll substitute all this in the integral and get the expression for work done. So work done by gravitational force, integral g m1 m2 by x square, that's the magnitude of force. Displacement ds, magnitude of displacement, we are writing as dx. Cos theta cos 180 is -1. That -1 I'm putting outside the integral. In fact, g m1 m2 also can be written outside the integral. And what remains inside is x power -2 dx. Limits from x1 to x2. Now what is integral x power -2 dx? Anyone?
X.
Your voice was cut. I could not hear properly.
-1 by x.
-1 by x, correct. And you substitute limits x1 to x2. Now that minus and this extra minus, see, this equal to is only for this term, not the entire term. Only this part becomes equal to -1 by x. Minus minus cancel, it becomes plus. So g m1 m2 into, substitute the upper limit first, 1 by x2, minus substitute the lower limit, 1 by x1. Okay. Now we took a situation where the particles were being taken away from each other. x2 is greater than x1. If x2 is greater than x1, 1 by x2 will be less than 1 by x1 and the whole thing becomes negative. Makes sense. Okay, this is what we want also. The work done should come out negative. Therefore, this is the proper formula for work done by gravitational force between two point masses, whose initial separation is x1 and final separation is x2. Hope this is clear to all of you. You can note down this formula. We'll be making use of this. Okay, negative in this case. It will always give you the correct sign. Okay, you substitute x1, x2 properly, you will always get the correct sign of work done. Okay, this is work done by gravity. Okay. Now listen, we are going to discuss one in-depth point, I would say. M1 was kept fixed here, and to derive this result, we conveniently assumed M2 was moved only along the line connecting them. What if it was moved in some other manner? Suppose you take M2 from here, where the initial separation is x1, to, let's call this position as A. Let's say M2 is taken from this position A to some random position here, B, where the final separation is x2. Now, during this displacement, okay, as M2 is taken from A to B, you visualize the forces acting on M2. When it is at A, the force acting would be like this. When it is somewhere between, let's say random position here, the force acting, okay, I can draw a dotted line between the two masses. The force will always be on that along that dotted line. It may become weaker, stronger, depending on whether it is coming closer or going farther, but it will always be on the line or along the line connecting the two particles. Okay. At this instant, the force will be like this. At this instant, the force will be like this. Now, these kind of forces, which are always directed towards one particular point, are called central forces. So gravitational force is a central force. And keep this point in mind. And this same idea we are going to use in electrostatics also, 12th class first chapter. Okay. Because electrostatic force shows the same behavior as gravitational force. Okay. So it's clear that gravitational force is a central force because the force is always directed towards one point. Now, when the force is directed towards that point, the displacement that matters in calculation of work done is the displacement along the line connecting the 2 points. Okay, what I mean to say is, let's assume the two particles to be somewhere here. You know the direction of the force between them. Okay, let's say that second particle is displaced from this position to this position. Now it's actually a very small displacement ds, but for us to be able to visualize, I have shown it as a significantly long vector. Now that small displacement ds can be split into two components. One component of ds along the line connecting them, and one component of ds perpendicular to the line connecting them. And that perpendicular component would be like this. The actual displacement is ds. I'm splitting it into two components. Okay. The component along the line connecting them, you can call it parallel component or the radial component. Like if you visualize all these lines, okay, lines of force, they all point towards one particular position. Okay, so you can treat that particular position as the center. Then these become the radial directions, radius. Okay, so you can split the displacement of the second mass into one component, the radial component, into another component, the perpendicular or the tangential component. For work done, calculation of work done, it is this component that matters, the component in the direction of force. The radial component is what matters. In the perpendicular direction, the displacement doesn't matter. Okay. Now, suppose M2 is taken from this position to some position here. All the displacements, all the small displacements along the way can be split into radial and tangential components. So you can assume this displacement like, okay. Yeah, you can consider the displacement like this: radial, tangential, again, radial, tangential, radial, tangential, radial, tangential. You can split the displacement into components, small displacement into components like this: radial component, tangential component. The work done during the total displacement will depend only on these radial components of displacement. How much it is effectively moving away from M1 or towards M1 is what matters. Only those green lines matter. Okay, the orange ones don't matter. Because work done depends on component of displacement in the direction of force. Okay. Now you imagine a circle having initial radius, having radius x1, and another circle having radius x2. Now, in the calculation of work done by gravitational force, it's only these displacements that matter, the ones that I'm highlighting in green. Okay. The displacements that I'm highlighting in green take the mass m2 from an initial separation x1 to a final separation x2 from the first mass. So this is m1, this is m2. Initially, their separation is x1. Finally, their separation is x2. You add all these green displacements, okay? It will just be equal to x2 minus x1. The radial displacement is what matters. So, irrespective of the path in which the particle is taken, irrespective of the path in which m2 goes from A to B, what matters for work done by gravity is how much it goes away from m1. So what matters is this distance. Okay, it doesn't matter how it covered that distance. It could have gone along this path, it could have gone along some path like this, it could have gone maybe like this. It doesn't matter how it goes. All that matters is from where to where it goes. Okay, therefore work done by gravitational force depends only on the displacement, overall displacement, not the path followed. What are such forces called? Can any one of you tell me? Forces whose work done depends only on overall displacement but not on actual path followed. What are such forces called?
Conservative forces, sir.
Good, good. Conservative forces. So this is the proof that gravitational force, even when it is variable, even in the form gm1 m2 by x square, gravitational force is a conservative force. See, earlier also we had used the fact that gravitation is a conservative force, but there in work energy power and system of particles, we justified that gravitational force is a conservative force because mg is constant. Constant forces are conservative forces. But here we know the force of gravitation changes based on the distance. Even if it does, it is still a conservative force because we now see that the work done depends only on the overall displacement, not the actual path followed. Okay. So even though this derivation of work done by gravitational force was done by assuming the second mass moves along that straight line, the result is valid in general. Okay. If the initial separation between two masses is x1 and final separation between 2 point masses is x2, this is the work done by gravitational force acting between them. Okay. That displacement doesn't have to be on a straight line. It can be in any direction. Initial separation and final separation is what you need to know. Okay. Now we have an expression for work done, and we just proved that gravitational force is a conservative force. And if you know work done by a conservative force, you can derive a formula for potential energy associated with that force. Now we had already discussed and used gravitational potential energy mgh. But when to use this formula? When the force of gravitation is constant mg, you can say potential energy is given by mgh, where h is the height above or below the reference. Okay. But in this case, now you know that gravitational force is a variable force based on the distance. So now you can't use mgh. Okay, so let's see how to find out gravitational potential energy for the actual formula of gravitational force. Okay, can one of you recollect and tell me what is the relation between, or what is the uh, basic definition of change in potential energy? How is change in potential energy related to work? By definition, what is change in potential energy equal to? Or,
Sir,
Saket.
negative of work done.
Correct. Good. Negative of work done by a conservative force. By using this, we had derived gravitational potential energy mgh, spring potential energy half kx square. Okay. This all that was done based on this basic definition of change in potential energy. Potential energy change is defined like this. Okay. Now we just derived a formula for work done by gravitational force. We got it as g m1 m2 into 1 by x2, that is the final separation between masses, divided by minus 1 by x1, that's the initial separation between masses. So when two masses are taken away from each other or towards each other, you know work done by gravitational force. And if you know this, you know the change in potential energy. Therefore, during this displacement, when m2 is taken away from m1 or towards m1, do something, okay? Bring them closer or take them farther, doesn't matter. The change in potential energy of the system is negative of this expression. So I'll include the minus, then 1 by x1 will come on this side, 1 by x2 will go to the other side. The formula becomes g m1 m2 1 by x1 minus 1 by x2. Okay, let us understand what this formula tells us. Consider two particles, m1, m2. Now, under the influence of their mutual force of gravitation, naturally, if you release this system, m1 and m2, m1, m2 will move towards each other. Okay. Not just a two particle system, any system in nature which is under the influence of conservative forces, any system in nature which is under the influence of conservative forces tends to go to a state of lower potential energy. Like spring you take. In which position does the spring have least potential energy? When it is in relaxed length. If you compress, it has energy half kx square positive. If you elongate also, it has energy half kx square positive. But you release the spring from a compressed state or an elongated state, it goes to natural length. Why? At that position, it has the least potential energy. You take an object to a certain height and you leave it, it falls to the ground. Why? Because when it goes down, its potential energy decreases. So not just these cases, even charges, like charges repel, unlike charges attract. They also do that because they go to a state of lesser potential energy. Any system which is under the influence of conservative forces naturally tends to go to a state of lower potential energy. Let's see if that happens here also or not. Now, these two masses, if you release them, they'll naturally come close to each other. Forces are inwards. Okay, these two purple arrows, they indicate the forces. Displacements naturally will also be inwards. If forces and displacements are inwards, that means work done by gravity, if they naturally come towards each other, work done by gravity will be positive. And if work done by gravity is positive, change in potential energy will be negative. Change in potential energy negative means potential energy decreasing. So as two masses come towards each other, the potential energy of the system decreases. Same thing happens with with a mass which is released above Earth also. It falls to the ground, means it is going closer to Earth. That is why its potential energy decreases. Okay, and let's substitute in this formula. If they are coming closer, x2 is less, final separation is less, initial separation is more. If final separation is less, okay, if x2 is less, 1 by x2 will be more. So 1 by x2 is high. 1 by x2 is high and 1 by x1 will be low. Low minus high, negative. So if masses come towards each other, their potential energy decreases. If they go away from each other, the potential energy increases. This is always true. Okay, under the influence of gravitational force, if masses come closer, potential energy decreases. If they go farther, potential energy increases. And this is the formula you can use to tell how much is the change in potential energy, depending on the initial separation and final separation. But remember, this is valid only for 2 point masses. Why? We derived this using work done by gravitational force between 2 point masses only. So you can use this for point masses. And we had learned that uniform spheres also exert forces or create fields just like point masses. Once you are outside the hollow sphere or a solid sphere, the sphere behaves like a point mass. We had discussed this. So this formula can be used for spheres as well. So this is only for 2 point masses or uniform spheres. For other shapes, you can't guarantee that this is applicable. What if the system has more than 2 point masses? What if the system is some other object like a ring or something? Then for every pair of point masses, you will have to find out. For one pair, this is the change in potential energy. If there are more than one pair being rearranged in a system, then you will have to find out change in potential energy of every possible pair to know the total change in potential energy. Okay. Let's solve a problem based on this. What can you use potential energy for? In energy conservation problems, you can use. So suppose there are 2 point masses. Assume one of them is m and it is fixed. Let's say the other one, okay, let's take them as m1, m2. Yeah. m1, m2, the initial separation between them, let it be d. m2 is released from rest. Now, if you release m2, m1's gravitational force will make it come towards m2. So force will act on it, it will accelerate. And as it accelerates, its velocity increases. So its speed increases, increases, and increases. By the time it covers half the distance, it would have attained a significant amount of speed. Okay. Derive its speed at this position. When it is at a distance, d by 2. So you know it is at rest initially. And at some other position, you are asked to find out the speed. And usually, how do we solve such questions? You have equations of kinematics, you have work energy theorem, you have mechanical energy conservation. One of you tell me, to find out this speed, after it covers a distance of d by 2, can we use equations of kinematics?
No, sir.
Okay, Vanilla is saying no. What about the others? Rishi, what do you say? To find out the speed attained by m2 after covering some distance, can we use v square minus u square is 2s? We know the displacement. Can we use it? Aishwarya, what do you say?
No.
Okay, why not?
So the acceleration increases.
Correct. The force as m2 moves towards m1, the gravitational force between the particles is not constant. As the distance changes, the force changes. And as the distance decreases, force becomes stronger. Acceleration increases. And if acceleration is not constant, equations of kinematics cannot be used. But still, you have some other ways to do it. You can use work kinetic energy theorem, which states that work done by all forces is equal to change in kinetic energy. Or if conditions are satisfied, you can use mechanical energy conservation also. What is the condition for mechanical energy conservation? Non-conservative forces must not be doing work. Now, what is making M2 move from that position from A to B? Gravitational force is making it move from A to B. Gravitational force, we just proved that it is conservative. So you can use work energy theorem or mechanical energy conservation to solve this problem. Okay. Do this, all of you. And those of you who have not noted, note this down. work done by gravitational force and change in gravitational potential energy when two masses are rearranged. If you want to use work energy theorem, you'll be using this formula. If you want to use mechanical energy conservation, you will need this. Okay, hope you have noted. Find out the speed of M2 when it covers half the distance. Do this, I'll give you all 2 minutes. Okay, Rishi, which method are you using? Work energy theorem or mechanical energy conservation?
Sir, mechanical and GM1 M2 into 1 by x1 minus 1 by x2.
That is change in potential energy. Okay, but the idea you want to use is mechanical energy conservation. Okay, I'll do it both ways. Follow this carefully, all of you. Suppose you want to use mechanical energy conservation. How you write the equation is initial potential energy plus kinetic energy of the system is equal to final potential energy plus kinetic energy of the system. Initial kinetic energy is 0. The particle was not moving initially, it was released from rest. Final kinetic energy, we can take it as half mv square, half m2v square, where v is what we are trying to derive. To get v, you need to know u1 and ui and uf. Actually, you don't need their original values. You only need to know ui minus uf or uf minus ui, any one of that. Okay. So you can say ui minus uf is equal to half m2 v square. Initial potential energy minus final potential energy is basically negative of change in potential energy, because change in any quantity is final minus initial. Initial minus final will be negative of the change. So minus delta u is half m2 v square. That's all. We have the formula for change in potential energy of due to gravitation. Minus the formula is gm1 m2 into 1 by initial separation minus 1 by final separation. You equate it to half m2 v square. Simple. You just have to substitute in this. Initial separation was d. Final separation is d by 2. So this becomes 1 by d minus 2 by d. That is minus 1 by d. Minus minus cancel. Left hand side you will be left with g m1 m2 by d. And right hand side you have half m2 v square. m2 gets cancelled. It doesn't depend on the particle's mass. You get v is under root 2gm1 by d. If you had used the work kinetic energy theorem, what would you have done? You would have written work done is equal to change in kinetic energy. Now work done by gravitational force is gm1 m2 1 by x2 minus 1 by x1 equal to change in kinetic energy. Change in kinetic energy is final minus initial. Initial is 0. That's all. It's effectively the same equation that you get. Okay. So in fact, we had derived in the chapter work energy power, we had derived mechanical energy conservation from work energy theorem itself. It's just another way of writing the equation under conservative forces. So whichever way you solve, you should get the same answer. And the answer here is under root 2gm1 by d. Okay. Fine. So this class so far we have derived an expression for work done by gravitational force, and based on that change in potential energy. Now that delta U formula is what we'll be using frequently. But sometimes you will be expected to tell what is the actual potential energy of a system, not the change. Now, how do we assign actual potential energies? Remember this, all of you. The actual potential energy of a system can never be determined. There's no scientific way to tell how much potential energy a system has. But if you assume potential energy at some configuration to be 0, then at another configuration, means at another arrangement, you can tell what is the potential energy. Okay, so you have to assign a reference distance. Like in gravitational potential energy, mgh also, first what we did was we derived delta U is equal to mg into delta h, if you remember. Then in problems, how do we apply? we choose some level as zero potential energy level. Then if certain level is assigned 0, then you can tell what is the potential energy at any other level. Okay. Same thing should be done with any kind of potential energy. So there's no proper way to tell how much is the potential energy of a system in one particular arrangement. When arrangement changes, potential energy changes. That you can tell. But if you want to tell exact value, then you have to take some arrangement as the reference. Okay. Now see, potential energy by definition is energy of interaction between two particles, between two masses. Gravitational potential energy. Now, when will two masses exert gravitational force on each other? Always they'll be exerting force on each other, but the force tends to 0 when the separation between the particles tends to infinity. Okay. So when separation tends to infinity, the gravitational force between masses tends to 0. So it makes sense to assume the potential energy at infinite separation to be 0 because there's no interaction. When there's no interaction, there won't be potential energy. Okay, or interaction is tending to 0, you can say potential energy is tending to 0. So what we do is, generally, when separation between the masses tends to infinity, the gravitational potential energy is assumed to be 0 or tending to 0. Okay. So consider 2-point masses. Let's say they are initially at infinite separation. M2 is initially at infinity. And from that position, okay, from a far away position, it is brought in to this new position, which is at a distance x0 or x. Okay, final distance is x. So let's say initially they were at infinite separation. Finally, they are at a finite separation x. Now, during this displacement, the system would have undergone some change in potential energy. Change in potential energy, that is potential energy at a separation x, final potential energy, minus potential energy at infinite separation, initial potential energy, is equal to, what's the formula? Gm1 m2 into 1 by x1 minus 1 by x2. Okay, 1 by infinity tends to 0. And at infinite separation, the potential energy also was assumed to be 0. Therefore, the potential energy at the finite separation x becomes minus g m1 m2 by x. You can use this formula to tell the potential energy, gravitational potential energy of a system based on its arrangement. Okay, but remember, this is derived assuming potential energy at infinite separation to be 0. And unless otherwise specified, this reference is always valid. Okay, if they particularly ask you to take some other distance as 0 potential energy, then the result will change, then the answer will change. If infinite separation is taken as 0 potential energy arrangement, then at any finite separation, this formula will give you the potential energy. And it makes sense also. Infinite separation, you are assuming it is 0. Now, when any two masses come closer, their potential energy has to decrease. That means from 0, it has to decrease. Therefore, gravitational potential energies will always be negative at finite distances. Okay. So you can use this formula to tell the gravitational potential energy between 2-point masses. You can use this between two uniform spheres also. Sphere and point mass also you can use. Okay. For other systems, you can't use this directly. So this is valid for point masses and our spheres. Okay. What if there are more than 2-point masses? Now this includes only two masses, M1, M2. What if there are more than 2-point masses? Then for every pair, you will have to find out the potential energy. Okay, let's solve one problem based on this. Note down this formula, all of you. Potential energy between 2-point masses which are at a distance x from each other is minus g m1 m2 by x. Okay, if infinite distance is taken as 0, then at any finite distance, it must be negative. Okay, Questions like this are very, very common. Assume there's an equilateral triangle with 3 point masses placed at its corners. M. Okay, let's take all 3 of them to be M to begin with. Let's say side of the equilateral triangle is A. Find out or calculate the total gravitational potential energy of the system. Do this quickly, all of you. There are 3 point masses here, and I gave you the idea already. If there are multiple point masses, you have to find out energy associated with every pair. So you think of how many possible pairs you can make out of these, and for each pair there will be a potential energy. Add all of them, you will get the total potential energy. Do this quickly, I'll give you 1 minute. Yusuf, can you unmute? Aishwarya, can you unmute?
Yes, sir.
So see, there are 3 point masses A, B, and C. First, tell me how many distinct pairs can you form with 3 objects?
So 6 pairs.
Distinct pairs means we don't want to count one pair twice. How will you get 6 distinct pairs from 3 objects? Okay, tell me the pairs.
Sir, AB, AC, and BC, sir.
That's all. Only 3 distinct pairs are possible. Correct. With 3 masses, you can form 3 pairs. And each pair will have a gravitational potential energy. Okay. See, basically the idea is this. Imagine the masses were not even present initially. Okay. We just have 3 positions. No masses are present. Now the masses have to be brought one by one from infinite separation to these final positions. Why from infinite separation? Because at infinite separation, we assume the gravitational potential energy to be 0. That's the distance where we know the potential energy. This is where we don't know the potential energy. Okay. So when the first mass is brought, when the first mass A is brought from infinity to this position, the other masses are not there at all. Okay. So no gravitational force would have acted on it. You can bring the first mass freely. No force would have acted on it. It won't get a potential energy at all. One particle on its own will not have potential energy. Potential energy is always associated with systems. At least 2 particles should be there. Okay. So first particle, no potential energy. I mean, single particle, no potential energy. Now, assume the particle B is brought from infinity to this position. As you bring B from infinity to this position, A will exert a force on it as it comes in. A's gravitational force would have acted on it. Okay. And because the gravitational force acts, these two will develop a potential energy between themselves. Whenever conservative forces act, then only potential energy will develop. So AB will have one potential energy between them. Okay. Next, assume the third particle is brought in from infinity. As you bring the third particle C from infinity to this final position, A's gravitational force would have acted on it during the displacement. B's gravitational force also would have acted on it. So AC will get or will develop one potential energy. That pair will develop one potential energy, and BC will develop one potential energy. Interacting particles will have potential energy between them. So which particles interact, how many pairs interact, you have to see. Therefore, the total potential energy of this system is potential energy of the pair AB plus potential energy of the pair BC plus potential energy of the pair AC. And what is the formula for potential energy of a pair of point masses? Minus G m1 m2 by the distance between them. So minus G, masses are equal, so m square, distance is A, and all 3 pairs will have the same energy between them, so into 3. Therefore, the total gravitational potential energy of this system minus 3 gm square by A. Okay. This gives you another way to define gravitational potential energy also. What did we just discuss? We assume none of these particles were present, and the system is assembled by bringing the particles one by one. Okay. When the first particle A is brought, work done by gravity was 0 because there was no other mass to exert a gravitational force on. Gravity itself was not there on A. Okay. So when the first mass is brought, work done by gravitational force is 0. When the second mass is brought, when B is brought, work done by gravitational force during that bringing process is gm square by A, positive work. As masses come closer, work done by gravity is positive. Okay. So gm square by A work is done. When the third mass is brought, when C is brought, A's gravitational force would have done work on it. B's gravitational force also would have done work on it. So what is the total work done by gravity? Gm square by A plus gm square by A. Therefore, as this system is assembled, okay, I'll write this here. As the system is assembled by bringing particles from infinity to their final positions, the potential energy of the system is negative of work done by gravitational force. Okay, because when you brought these masses from infinity one by one, what all work was done by gravitational force? Gm square by A, gm square by A, gm square by A. Work done by gravity was 3gm square by A, and we see that the potential energy is just the negative of that. So this is another way to look at potential energy of a system. It's the negative of work done by gravitational force to assemble the system or while assembling the system by bringing the particles from infinity to their final positions. Okay. So with 3 masses, you can form 3 pairs. So that will be the potential energy of that 3 particle system. Next. One of you tell me, if there are 4 particles, how many distinct pairs can be formed using 4 objects? Think carefully and tell. How many distinct pairs can be formed using 4 objects?
Six.
Good, correct. 6 possible pairs. Okay. AB, AC, AD. Then B has already been paired with A, so it can still be paired with B and C, B and D. And the last pair possible is C and D. So 6 distinct pairs are possible. Basically, to find out how many pairs can be formed, how many distinct pairs can be formed from different objects, you can use this formula NC2. I think this is how it is written. Or do they write it this way? Okay, I don't exactly remember which way it is written. Have any of you learnt binomial theorem, permutations, combinations? Do you know the formula for NCR? I think it's written this way. Okay, if you don't know, leave it. I don't want to confuse you.
Sir, it's n factorial by r factorial into n minus r factorial.
Yeah. I think you'll learn that in 12th class or maybe towards the end of 11th class. From a given set of objects, you want to form pairs means you have to choose 2 of them. Okay. So how many combinations, how many different combinations of 2 objects can you form from a set of n objects? It is represented as NC2. Rishi, is this the right way to write it, or should n be below and 2 be above?
Sir, n should be above only. R
Okay,
will
this
be
is
down.
fine. So the formula will be n factorial by r factorial into n minus r factorial. Okay. And what is factorial? It's the product of all natural numbers from n down to 1. Okay. Now here there were 4 objects. So the number of objects is 4. And you need to make combinations of 2 objects. Pairs means 2 objects. So the number of pairs that can be formed is 4C2. That is 4 factorial. 4 factorial is 4 into 3 into 2 into 1 divided by 2 factorial is 2 into 1 into 4 minus 2 whole factorial. 4 minus 2 is 2. 2 factorial is again 2 into 1. 2 into 1, 2 into 1 cancels. Again 2 and 4 cancels. 2 into 3, the answer is 6 pairs. So from a given number of objects, if you want to know how many pairs can be formed, you can use this formula. NC2, that is n factorial by 2 factorial into n minus 2 whole factorial. But anyway, in physics, they won't trouble you that much. Up to 4 objects, you remember. 4 objects, you can make 6 pairs. Okay. Try another question. So now you know how to write the potential energy of a set of point masses. 3 point masses we discussed. Okay. Suppose there are 2 point masses. Okay, M and M fixed. And a third point mass is released on their perpendicular bisector from rest. Third point mass, let's assume it is 2m. It is released from rest. Can any of you tell me what is going to happen? What will happen after 2m is released from rest?
So 2m will move down.
Okay. See, in this chapter, fine. On your screen, it looks like it's going down. That's okay. You should say 2m will move towards the center of the 2 masses. Okay.
Or the gravitational force of M, both the M's will act on 2M.
Correct. Under the influence of that gravitational force, it will move towards the center. Equal amount of force will be there on both sides. There is a symmetry in this situation. One force this way, one force this way, effectively makes the mass move this way. Okay. As it moves down or towards the center midpoint, it will gain velocity. I want you all to find out with what velocity it will arrive at the center. Like when it gets here, what speed will it have? And for that, you need to know the distances. So let's say this distance is 2x. There's a symmetry in this situation. On the other side also, it will be 2x itself. And assume this is x and this is x. Okay. Find out the speed of the particle of mass 2m when it comes to the midpoint of m and m. I'll give you all 2 minutes. Make it fast. Now 2m moves because of gravitational force. So you can apply mechanical energy conservation, and that is what we are going to do. Ui plus ki is equal to uf plus kf. Now this system as a whole, if you see, there are 3 particles. But between 2 particles, there is no change happening. Okay, you can name these as A, B, and C. The arrangement B and C is not changed at all. Now B and C will have a potential energy between them. But how much ever potential energy B and C have initially, they'll have the same potential energy between them finally also. So if you write it in the equation also, it's going to get cancelled. So we won't be doing that. We'll only be taking potential energy of A associated with the other particles. Okay. Now A and B will have one potential energy between them. What is the formula? G m1 m2 by x with a minus sign. So initial potential energy of this, okay, between A and B will be minus G. One mass is m, the other mass is 2m, divided by the distance between them is 2x. And with C also it will have the same. So into 2. That's the total potential energy of A initially. Okay, just for convenience, we say this is the potential energy of A. It's actually potential energy between A and B and between A and C combined. Okay. Kinetic energy is 0 initially. A was released from rest. Finally, when A comes to this position, it will have one potential energy with B, one potential energy with C, each of which will be minus, again, G into M into 2M. So I'm writing it as minus 2gm square by X, because the final separation between A and B or A and C is X. And there are two such potential energies. And kinetic energy will be half into A's mass is 2m into E square. That's all. You just have to simplify this equation now. 2 gets cancelled. Here also 2 gets cancelled. You simplify this, it becomes minus 2gm square by X is equal to minus 4gm square by X plus mv square. M gets cancelled. 2g by X, 4g by X effectively becomes 2 capital G by X. 1 m will be there, is equal to v square. I am getting under root 2gm by X. Wait, let me check. Minus g m1 m2 by distance is 2x. There are two such pairs, so into 2. So minus 2gm square by x will be left on the left hand side, is equal to right hand side minus g m into 2m. Yeah, I think this is correct only. Those of you who gave the wrong answer might have made a mistake with this. I mean, this is a very common mistake actually. Final kinetic energy, blindly students write half mv square, but we are finding out the kinetic energy of 2m. So you have to take half 2m into v square. Okay. So today's class we have discussed how to find out work done by gravitational force and the potential energy due to gravitational force between two point masses. You can extend this to spheres also. Uniformly distributed spheres can be done. Next class, we'll discuss how to find potential energy between a ring and a particle. Okay, I don't think we have to discuss it separately. I'll give you that question in the worksheet. Do that. Next class, what we'll do is we'll apply all these ideas, gravitational field and potential energy, these ideas to an actual system, which is a planet and a particle nearby. Okay. So next class, we'll discuss how much gravitational force a planet exerts on a particle nearby or an object nearby, how to find out the acceleration due to gravity of a planet based on the mass and size of the planet. Okay. And then when you release an object near a planet, what will happen to that object? With what speed it will hit the planet and such things. Those will involve energy conservation. Okay. So again, it's important to solve tomorrow's worksheet, and yesterday's worksheet, only one of you, only Aishwarya has sent the answers. Others also do it. Okay. Some important ideas are there. You need to know how to apply ideas. No, if you don't solve problems, then attending classes will not be useful. Like just listening a class is never useful unless you apply what you learn. So try to solve some problems. Just attempt those questions once. Even if you don't get the answers, it's fine. Attempt them and send your answers to me. I'll tell you whether they're correct or not. Fine. We'll continue in the next class, which will be on Wednesday. Okay. Thank you all, and advance Happy New Year to all of you.
Thank you, sir. Thank you.
Thank you, sir.